So hi everyone, thank you for coming to listen. We are from Lehigh University and we're going to be talking about our project in STEM learning through visualization that we have run through the Office of Creative Inquiry at Lehigh University. And all the work we talk about today can be found on our website, and all the code can be found on our GitHub repository linked here. So I am Anna Marini. I am a senior at Lehigh University and I'm studying statistics.
My name is Brian Lucas and I'm a junior at Lehigh University studying chemical engineering. The advisors who are directly associated with this project are Professor Rangarajan from the Department of Chemical Engineering at Lehigh, Dr. Tyagarajan, who has been of immense help with us, but he is not affiliated with the university in any way. And then the other person who has been of immense help to us is the late Professor Grassi, who is from the Lehigh University Chemical Engineering Department.
We also had some assistance from people outside of our project. So Dr. Angela Brown, Dr. Lori Hers, and Professor Bill Scheisler are all Lehigh University professors, and Steve Anthony from the Lehigh Technical Services have all helped us in some way with our project.
So the reason why we took on this project was, anecdotally speaking, and from my own experience, STEM subjects and people in STEM majors, there is a fairly low retention rate for people in STEM fields. So a lot of people tend to change majors pretty early on, who are studying STEM subjects. And then with that, there's also a lack of access to experiences inside labs. And so given the current situation with COVID-19, the accessibility to labs is even more restricted. So by doing this project, we're able to kind of enhance a student's ability to personally interact with material and give access to, that interactive experience that they might not be able to have. So far we have 3 models that are currently being hosted on our website that people can access. The first model is a reaction kinetics model for sequential reactions. The second model is a thermodynamic and heat transfer model that deals with a zero energy cooling chamber. And the third model that we have currently hosted on our website is an infectious disease model that details the spread of an infectious disease.
So I'm going to walk you through our infectious disease model a little bit more. So it's an SEIR infectious disease model, which is based on a system of differential equations. So for our model, we have 8 classes and therefore 8 differential equations. And our classes are susceptible people, exposed, and then we have 4 infected classes, recovered, and dead. And the 4 infected classes, we separated them out due to different potential rates. So we have in asymptomatic and unknown infected, in asymptomatic and known infected, symptomatic, infected, and non-hospitalized, symptomatic, infected, and hospitalized. So when you open up the SEIR model on our website, this is what you see. And on the left, we have a network graph, and on the right is a bar graph, both of the class populations for each of the 8 classes. And then there's this time slider with a pause and play button. So when the user hits the play button, the program will start iterating through time and show how each of the class populations changes. And the user can pause this and drag the time slider to a specific value if they want. And these graphs also have some interesting capabilities that we are able to add. So if a user hovers over an edge, a description will pop out describing how an individual moves from one class to another along that edge. And on the bar graph, the user can zoom in and they can hover over the bars to get the current class populations. And then we also just have some additional information below. So then there's a second tab, which is a sort of build your own infectious disease, where the user has the ability to change different parameter values such as infection rate, recovery rate, or introduce a vaccine. And the graph will automatically update to reflect these parameters and changes. So the top graph has all 8 of the class populations over time, and the bottom graph just displays the 4 infectious classes to get a more zoomed in look. And then the table on the right just displays all the current parameter values being used for the current model displayed. The user can also hover over parts of these graphs to get population values at the specific time on the x-axis. And then we included one final tab just with some further information about the processes involved in this model. So I'm also just going to explain a little bit more about how we were able to use the Bokeh package in Python to include these interactive aspects in our model. And so it's kind of a cycle, and I'm just going to include some of the code snippets and talk you through. So the first step was setting up the data and the initial conditions. So this code on the right is just a bunch of the initial parameter values we had to set to have our base model to build off of. And then the code below is setting up the network graph. So creating all of the nodes and their initial sizes and location, and creating the edges between certain nodes. So the second step is plotting these initial conditions. Like I mentioned, the infectious disease model is based off of a system of differential equations. So the solve IVP function solves this system of differential equations over the time span, which we use of 365 days. And this stores each of the class will be stored in a vector that includes each of their population values through the 365 days in time. And then this here also includes setting up the time slider and setting the initial sizes of the nodes. So then the last big aspect of this is how the user can interact with the model and the code that supports that. So this first function on the right, update data bubble, gets the current time at the time slider and then retrieves each of the 8 class populations at that given time and updates the network graph and the bar graph to display the current class population. And then the next 2 functions on the left here kind of deal with the pause and play button. So the animate update function automatically iterates through time. So it'll take a time value, display each of the 8 class populations accordingly, and then automatically move to the next time unit and display those again and again. So then that's used within the animate function, which calls the animate update function to stop or start iterating when a user presses the pause or play button.
So as mentioned previously, we do have 2 other models currently being provided on our website. So this is the dashboard that one looks at when you're doing the reaction kinetics model. So on the left are the sliders where you can adjust the different values. And so the graphs automatically update as well. So it allows you to basically see the concentration over time for 2 sequential reactions. The next model that we have is a model for a zero energy cooling chamber, which is a cheap and effective way for storing food. And it is based off of evaporative cooling that passively cools food on the inside of this chamber. So this is the dashboard that one would look at during the zero energy cooling chamber model. So with this, you are able to view data that we provide on the dashboard. And so students are able to kind of use this in while using the model to help guide their decision-making process while using this. So as you can see, there are sliders and adjustable values and parameters. And then in the bottom, there's a table where you can tabulate data and keep a record of each parameter value as you're adjusting it. So in this process of making these models, we also took surveys of students to get an understanding of how the user experience was. So overall, it was a very positive result that we received. So the overwhelming majority of people found our models to be clear and useful, and they understood the meaning of it. And furthermore, every single person who we surveyed was actually able to access the models as presented on the website from the devices that they used.
All right, so thank you everyone for listening to our talk today. We are excited and eager to answer any questions or comments you may have about the specific models or project in general in the Q&A portion of this talk. Thank you.